Hello everyone, I hope you had a wonderful day and welcome back to the channel. I'm here again with another video and another subject which I believe is very practical and can be very helpful for your projects. As you know, LLAVA has been one of my favorite models. It is a multimodal large language model. I've already used it in my previous projects. In this video, I want to show you how we can fine-tune it on custom datasets. Besides that, I want to also show you how we can fine-tune it in a way that it can extract structured data from images. As you can see, we are going to cover a lot of information, but I will make sure to include the links, the URLs, the references, everything in the description of the video, and also I will include them in the README file of the GitHub repository. So first, let me show you what I mean by extracting information from the images. So by the end of this video, we will have a fine-tuned LLAVA that is able to extract JSON information from an image, a receipt like this. So we will design this dashboard and we can upload our images in this dashboard, and our model will extract the information with a structure that we will teach the model throughout the fine-tuning process. So in this video, I will quickly go through LLAVA itself. I will explain the model, an overview of the model. Then we will discuss the fine-tuning pipeline, the steps that we need to go through in order to fine-tune a large language model or a large multimodal language model. And we will talk about the key considerations. Then I will show you two different ways that you can prepare your datasets to fine-tune a multimodal language model. Then we would go through the LLAVA architecture. This is something that I found it interesting personally, and I think it would be interesting for you as well. And finally, we would go through the whole process from data exploration up to the point that we would deploy the model and design the dashboard that we just saw. LLAVA was initially introduced in October 2023. It was called LLAVA 1.5, and then I believe around May 2024, they introduced LLAVA Next, which is the model that we will use in this project. So essentially, the LLAVA Next is an improved version of LLAVA 1.5. It has a higher image resolution and it supports more aspect ratios. And you can see the resolutions here. It has a better visual reasoning. It has better visual conversation, and it has better word knowledge. So these are the key differences between LLAVA Next and LLAVA 1.5. And you can find all the information with regard to this model on the HuggingFace. They also have GitHub repositories. They also have a playground for the model, and you can test the model. You can upload your own images and start asking questions from your images and see how the model would perform. And also you can use one of their templates and examples. Here you can also get a good idea of some of the use cases that the model can have. For instance, here they are asking what is fun about these images. In the second example, we want the model to summarize the main information from these images. Here we are asking who drew these paintings. Can you provide a brief description for each of them? And these are two CVs. So as you can see, let's say the performance of the model can be quite diverse, and it can give you answers based on different images. So let's go with one of these examples and see how the model would perform. The other thing that you probably notice is that the model can handle multiple images at the same time, which is a nice feature. So let's see how the model would perform on this example. The images are humorous because they depict birds engaging in human-like activities. So as you can see, the model is able to comprehend the images and give you a very neat and, let's say, reasonable answer. So when it comes to fine-tuning large language models and multimodal models, there are some steps that you need to take regardless of what model are you going to use and also what data are you going to prepare, which is something that I've already discussed and talked about in one of my previous videos. So this is a pipeline that I showed when we wanted to fine-tune large language models on a synthetic data that we created for a company named Cube Triangle. And we processed our datasets and created question answer pairs, plain text, and instruction response pairs. And we fine-tuned our large language model. I believe we fine-tuned 3 large language models to see the improvement as we choose a bigger size model for fine-tuning. So when it comes to fine-tuning multimodal large language models, the process is more or less the same. The biggest difference, as the name suggests, is that with multimodal large language models, the data is a combination of images and text together. So let's go through some of the key aspects for fine-tuning. So when you want to fine-tune a model, there are a couple of considerations that you need to take before jumping into writing the code or fine-tuning the model itself. The first one is the data and the data pipeline, which in my opinion is probably the most important step, because the data quality determines the performance of the model at the end of the day. So here I'm not going to go into the ML ops, let's say side of fine-tuning, but I will just talk about these aspects in general, and we would go through them just so we can fine-tune our model in this video. So the first one is the data pipeline. Then you need to define and figure out the GPU, the RAM, the storage that you would need for fine-tuning your, let's say, the specific model that you have in mind. Then the training configuration, which by itself, again, is something that requires a lot of testing, evaluation in order to find the optimum configuration for training. And finally, the training pipeline as well. So here I just want to mention the resources that are required for this specific project. For this project, I'm using a GPU with 80 gigabytes of VRAM. And for the GPU, I'm using Hyperstack Cloud GPUs. Hyperstack is a framework that is powered by Next-Gen Cloud. And I've already prepared my virtual environments. Everything is ready for me to run the code. But in case you want to set up the virtual machine and the environment so you can run the code as well, there are some steps that you need to take. And I'm not going to go through those steps, but I've already prepared all the steps for you here, so you can pause the video and go through them one by one. On the top, you will see the steps for setting up a virtual machine on Hyperstack. Then you can see the steps that you need to take in order to connect your VS Code to the virtual machine remotely. And here on the right, you will see the dependencies that you need to install on your virtual machine. I've already provided you with the requirements.txt in the GitHub repository, but there is one specific library that you need to install by yourself, which is the transformers from the HuggingFace repository. The reason behind that is we are going to use some of the features with transformers library, and those features are pretty new, and you only can access those features if you install the library using their GitHub repository. So again, in case you're interested to set up the environment, please feel free to pause the video and go through these steps. There should be no problem, and you should be able to easily set up the environment and run the project. In the next step, I want to talk about the datasets and how we can prepare them for fine-tuning a multimodal large language model. As I mentioned in fine-tuning pipeline, for instance, when we were fine-tuning a large language model, we had a couple of options with regard to the structure of the input data for the model, just like Q&A, instruction response, and also plain text. So when it comes to multimodal large language models, again, there are some options that you can choose from and prepare your data according to one of those tasks and options. So in this video, I want to show you two of them, but I will only use the one on the top for data parsing, because that is the main objective of our fine-tuning here. So there are two datasets that I'm going to cover in this video. The one on the top, which is called CordV2, and the one on the bottom, docvqa. As you can see, CordV2 is a dataset that you can use for data parsing purposes. This is an example from the dataset, and this is the ground truth for this specific example. So this dataset contains pairs of image and a structured text. As you can see, we have the text in a structured format, like JSON format. And this is the dataset structure itself. So here you have access to 800 examples for the train set. You have 100 examples for validation set, and you have 100 examples for the test set. So one important aspect here is, for this specific dataset, we don't want the model to just randomly get something from the user, but the way that we are going to fine-tune the model is we will teach the model that whenever it's received extract JSON in this specific format, the model should be able to extract the JSON information from that image and give it to us, just like what we saw on the dashboard in the beginning of the video. So this is the input that the model would receive. Of course, the tokenized version of this input, but this is where we are heading. So we want to prepare our data in a way that we can pass it to the model like this. For docvqa, which is a dataset for question and answers for specific images, this is an example from the dataset. And on the left, you would see the questions for that specific image. As you can see, questions are available on 5 different languages, and the model response for that specific image. For instance, here, which corporation is mentioned on the letterhead, and the response should be Great Western United Corporation. So these were the 2 tasks that I wanted to show you here, but of course there are other ways that you can fine-tune the model. For instance, you can fine-tune it for summarization purposes, or you can fine-tune it to extract information from other images. As you just saw in the playground, the model already knows how to extract information from resumes, for instance, summarize images, etc. But you got the point. You can fine-tune it for various purposes. But in this video, I will just go through these 2 datasets, and eventually I want to use Core V2 for fine-tuning. One very important thing is, depending on the task that you want to fine-tune your model, the input prompt would change. So as you can see here, I have put extract JSON as a static query, but here the user can ask various queries depending on the image that the user sends to the model, and then the model would generate the response for us. Besides that, you can also fine-tune the model for various languages. Here in this video, I would only pass the text in English language, but you can also fine-tune the model for different languages as well. So in the next step, let me quickly go through the structure of the model, and then we would jump into the code and we would see how we can fine-tune the model. I would briefly go over this topic because this topic is quite complex, but in case you are interested to read all the details, please feel free to pause the video and go through them. So as you can see, the model has 3 main pieces. The one in the first part of the model is a vision tower, which is a version of Clip vision model, and then the model has a multi-modal projector, and then finally the model is attached to a large language model. So I looked at different architectures of different models with various number of parameters, 7 billion up to 34 billion parameter models. As the name suggests, the main difference occurs in the large language model side, especially in these linear layers. As you can see here, for instance, for this specific model, which is the 7 billion parameter model, we have 1024 in these 2 layers. But I saw that, for instance, in 13 billion parameter model, the number of neurons in these layers are increased, and you can see the differences in the large language model side of the architecture. So just to give you an idea of why that architecture was designed, the vision transformer, which is designed to process the inputs, the images, it uses a variant of Clip. So it has an embedding side, then it follows by a pre-layer normalization layer, then it has the encoder side, the Clip encoder side, to inside that vision transformer, which consists of 24 Clip encoder layer, and each one of those encoders have their self-attention mechanism, their layer norm, and their multi-layer perceptron. Then on multi-modal projector side, which is the part that we want to use to project the visual features into a space that can interact with the language model. So it consists of 2 linear layers with an activation function in between, and that's it. So just like that, we can merge image features with text, and we can interact with the large language model. And of course, on the large language model, we have the embedding, and then we have 32 decoder layer. So in this case, they are using Mistral large language model for the 7 billion parameter model. And each one of those decoder layers has their attention mechanism, their embedding, and their multi-layer perceptron. And finally, we have the head of the large language model. I always get fascinated by seeing how these architectures can communicate together and allow us to perform such complex tasks with a very high precision. And I just wanted to share some of the thinking behind the scene of how they designed LLAVA in the first place. So that being said, let's jump on the code and see how we can fine-tune our multimodal large language model. So this is the project. As you can see, I'm already connected to the virtual machine. Again, I will be using an A100 GPU with 80 GB of VRAM. So make sure that you have enough VRAM on your machine. So this is the project structure. It is very similar to my previous projects. We have the source that contains the dashboard that I just showed you. We have the notebooks that we are going to go through them one by one, data exploration, fine-tuning, and testing some models. And this is the environment. So you won't have the environment in the GitHub repository. You have to create it by yourself. I already showed it to you on those steps that I mentioned earlier. We have the data. These are some sample data that we want to use when we design the dashboard. And let's begin by going actually through some of the models and see how they would work. So here in the test models, I have provided you with multiple notebooks. As you can see, you can test various LLAVA models based on the specifications of your machine. So you have from 7 billion up to 34 billion. I tested all of them. I've also provided you with external resources in case you are interested to read more about these specific models and go further than what I've provided already in the notebooks. But for instance, let's test this model. So this is LLAVA 1.6 7 billion parameter model, and let's see how it works. And at the end of this notebook, I also want to show you how it performs on one of the examples in our dataset without fine-tuning. So I just ran both LLAVA 1.6 Mistral 7 billion and LLAVA 1.6 Vicuña 13 billion because I want to show you their difference and compare their performance on our test example at the end. So let's go through one of them. Both of them are identical, but at the end I will show you the results. So in LLAVA 1.6 7 billion, first we are going to load the model. I'm loading the quantized version of the model. In case you are loading the quantized version, you would need around 8 GB of GPU or 9 GB, more or less. And in case you run the full model, you would require 24 GB of GPU for inferencing. Then I'm just printing the model architecture. Next, I'm preparing an example. It is not from our dataset. It is just an external example. So we see how the model would perform. So this is an image that I prepared. And then I'm asking, what are the things I should be cautious about when I visit this place? And what should I bring with me? Actually, this is one of the examples that the LLAVA team themselves provided in their notebook. I'm using it because I really like the idea of the model suggesting you how to be careful when you go to this place. So as you can see, the model comes back with a range of suggestions. So first the question, and then here is the answer. When visiting a place like the one shown in the image, which appears to be a Syrian lake with a dock and surrounded by forest, and then it started first take your safety gear, then weather preparedness, then navigation tools, etc. This is fantastic. The model is able to understand the whole concept of this image and give you suggestion on how to be careful when you go into that place. Next, these multimodal models, they don't work only with a pair of image and text. You can also pass text only to those models. This is an example. I'm just simply asking the model to tell me a joke, and the model gave me an answer. Why did the tomato turn red? Because it saw the salad dressing. So here I want to test the model on Cord V2, which is the dataset that I want to use for fine-tuning of LLAVA 1.67 billion. So for the first example, this is the image of our example. As you can see, it's a little bit shady, but it has real ganache, I believe, egg tart, pizza toast, and the total of 45,500. So when I ask the model, extract JSON from this image, the model says the image you have provided appears to be a receipt from a restaurant. However, due to the quality and angle of the photo, it is difficult to read the text clearly. If you need assistance with reading the text or extracting the information from the receipt, please provide a clearer image or type out the text you need to help with. So the model failed to extract the information from the first image. Let's give the model another example. This is a second example. This is not shady. I would say it is more clear. So let's see how the model would do. The image you have provided appears to be a receipt from with some personal information and transaction details. However, due to the nature of the image and the presence of personal information, I'm unable to provide a JSON extraction. So the 7 billion parameter model refuses to extract JSON even if the image is clear. So if we can fine-tune the model in a way that it gives us the JSON in the output without any question and without hesitation, that would be a great accomplishment. Let's see the 13 billion parameter performance on the same examples. So for this example, the 13 billion parameter model gives me this answer. The receipt lists the following items, and first I'm asking what is shown in the image. It gives me an explanation of the information inside the image, and then here I'm asking it to extract JSON. So as you can see, this model actually provided us with a JSON from the content of the image, although this is not the structure that we want to use at the end, and we would teach the models a specific structure so we can get the JSON in that format. Let's see for the second example. This is the example, the same example that the 7 billion parameter model refused to give us the answer for it. So if I ask extract JSON, again, the 13 billion parameter model gives us a JSON output, and indeed the values are correct and the information is correct. Let's just test the total, which is 27,000, and the receipt ID, which is 404. So actually the receipt ID, although it is blurred, the model was able to extract the information, which is fantastic. And on the other side, the total is 27,000. So actually it is 23,000. So the total was 23,000. The total for the second part is 27,000. So this is interesting. The model is actually able to give us a JSON output. So that is the main difference between a 7 billion parameter model and a 13 billion parameter model. So since the 7 billion parameter model refused to give us an answer, even if the image is clear, I want to use that model for fine-tuning so we can clearly see the difference between the model without fine-tuning and the model after fine-tuning. If we pass the same images, these images are coming from the validation set, so we will pass the same images and see how the model would perform on these images after we fine-tune the model. So let's move forward and let's go through the data exploration. In the data exploration folder, I provided you with two different notebooks. One goes through Code V2 and the other one is for docvqa. So here I would go through Code V2 in detail, but feel free to go through docvqa. I performed the same analysis, almost the same analysis, and I would just briefly mention the differences and how you can prepare it for fine-tuning, but eventually my main focus would be on Code V2. So let me run this notebook completely, and while it is being executed, let me quickly show you what we are going to do here. So I divided the fine-tuning procedure into three different steps. As you can see, we have the data prep pipeline, the training pipeline, and the fine-tune testing the fine-tune model pipeline. I'm calling them pipeline, but actually they are just simply notebooks that I'm going to use for this video, but this is just a schema to give you a better understanding of what we are doing in each notebook, and you can follow along easier. So in data preparation pipeline, we are going to go through these steps. We are going to load the data set. We are not going to clean the data. The data is already cleaned, but this is just a typical step that I put there. We are going to explore the data and understand the structure and understand how it is designed. Then our grant routes are all in a string format. We would convert the strings to JSON format, and then we would convert the JSON formats to a token format that is understandable for the model. So again, we would see the function in the notebook. Then we would store all the, let's say, tokenized ground truths in a list. And finally, we would design a LLAVA dataset class that gets the loaded datasets, applies all these steps automatically, and gives us the train dataset and the validation dataset. So let's go through these steps and see them one by one. So before we proceed, I should mention that in order to fully understand what is happening from now on in data preparation up to fine-tuning the model and deploying it, you need to have some experience working with PyTorch and HuggingFace libraries. And I assume that you have already fine-tuned or trained a model, because the concepts are very complex and it's just outside the scope of this video, and I cannot go into the detail for every single step. But I will mention the key steps that are needed for fine-tuning LLAVA, and in case you have some experience already, that would be easy for you to catch up. You already should know that when we train a model or fine-tune a model in PyTorch, we are using data loader in order to process the data and pass it to the model in batches, or let's say one by one. In data loader, we have a train dataset and a validation dataset here. And these two objects are responsible for processing and applying changes to each one of the samples in Core V2. So the objective of this notebook is to show you what are those changes and what is the processing that is required for each samples of Core V2. And if you go down into this notebook, you would see that I have a class called LLAVA dataset, and using this class, I'm creating these two objects, the train dataset and validation dataset. So the objective of this notebook is to explain what is happening inside that class, and I'm going to break it down for you, and I'm going to explain all the steps that are necessary and all the changes that are required for the preparation of our data. So first I'm loading the data, and then I'm loading one example from the data. As you can see, it contains a pair of an image and a ground truth. So this is the image. And for this image, we have a ground truth, which is something like this. So as you can see, our ground truth is initially a string. That string contains a dictionary, and this is the pretty print of the same ground truth. As you can see, we have a string, and that string holds a dictionary. That dictionary by itself is a nested dictionary. So we can simply extract and convert that dictionary into a JSON data using JSON loads. So this is what I'm doing here. JSON loads, I'm converting it to JSON, and now I can treat it as a dictionary. I can loop over it, I can extract keys, and I can do whatever I want with that JSON object. So this is the ground truth, but now I'm going one step further and I'm extracting the GT_parse from that ground truth. So in my ground truth, I'm mainly interested in a specific key called GT_parse, and this is what I'm going to process and prepare for my model. Our ground truth has other keys as well, such as meta, but we are not going to use it for fine tuning. So here, again, as you can see, I'm converting it to JSON, and then we are going to loop over it. Ground truths for LLAVA in general can have two different scenarios. You can either have multiple ground truths for a specific query, or you can have one single ground truth for that query. So for Core V2, we will not deal with a scenario where multiple ground truths exist for a specific query. So I would not explain it for Core V2, but then I will explain what is happening and how should we address it for LLAVA. So in case of Core V2, all of our ground truths would be a dictionary, and we are just going to wrap it up in a list and store it in GT_JSONs. This is how we are doing it here. Then we are going to pass that list, which contains a nested dictionary in it. This is a list that contains a nested dictionary to a function called JSON to token. So let me read from here because it is easier for you to understand. The JSON to token function is designed to convert a JSON object into a string that represents a sequence of tokens. The function handles different types of JSON structures, including dictionaries, lists, etc. But we are mainly interested in dictionaries here for this specific dataset. The main idea is to create a flat token sequence that captures the structure and content of the JSON object. How do we do it? Handling dictionaries. If the dictionary has only one key and the key is text sequence, the function returns the value associated with this key directly. Again, this is not the case for Core v2. This function is designed for similar datasets, but with different scenarios. What happens in Core v2 is, for each key, the function wraps the tokenized representation of the value with tags, with these two tags. And these tags are used to delineate different sections of the JSON structure, similar to how HTML tags work. The function recursively calls JSON to token on the value associated with each key, allowing for nested dictionaries to be processed. This is what is happening with Core v2 dataset. The rest of the scenarios where we have a list or where we have text sequence they are not happening in Core v2. I will explain them after I finish explaining Core v2 preparation. So these are some examples that I provided to you. You can see that if, for instance, we pass this dictionary, or let's say this part of the ground truth to that function, this is the output. And again, another example. And here I'm merging the previous two examples because eventually we are passing it a nested dictionary. So this is our function. So if I pass this raw JSON to that function, this is what I get in the output. And the key takeaway is, if we pass this to a model, the model is going to learn to produce this format in the output. So just keep it in mind that when the model receives an image, for that image, it's going to generate something like this. So eventually we would need another function that reverses all these changes and give us a nice JSON structure like this one. Okay, and we just wrap them up in a list. Let's move forward. Here we go. This is the full class called LLAVA dataset. In this class, we are doing all the steps that we just saw earlier on one example, but this time on all the examples inside our dataset. So this class is inherited from the dataset class from Torch. And as you already know, from this class now with getItem, we can start requesting datasets. Let's say we can start getting image text pairs and pass it to the data loader. So this is the train dataset and the validation dataset constructed using this class. And if I show you an example, this is an example within those objects. These are the top 10 examples. And this is how we prepare each input for the model. So as you know, models require a specific structure. You have to make sure about the structure of each model before fine-tuning it. For LLAVA 7 billion, this is the structure that we are going to use. As you can see, extract JSON is a static query that I'm putting here. And then we pass the ground truth that we just created earlier, and we pass it to the model. This is the function that I mentioned earlier we would need in order to reverse back the model's output into a JSON structured data that we can use later. So I'm not going to go through it, but if I pass the prompt that we just saw earlier, let me print it for you. So this would be, let's say, an example for the model output. If I pass it to a function, that function would give me a nicely formatted JSON output, and I can do whatever I want with that JSON output. So this is how we prepare Core v2 before passing it to the data loader for fine-tuning. There were two other scenarios. I will skip one, but I want to address the one that I mentioned. There might be a scenario where we have a list of ground truths. So in case in your dataset, you have multiple valid answers for a specific query, that means you have a list of ground truths. So what you would do essentially is you would convert or process each one of those answers. Depending on your dataset, you might need different processing procedures. And then when you pass it to the model, you would randomly pick one of those answers for that query for each epoch. So that is how we handle a list in case your dataset has multiple answers for query. This is a scenario that happens in docvqa. If I show you, for instance, here, for this specific query, as you know, we have queries in 5 different languages. So let's find out the English version. What is the name of the tobacco company? As you can see, we have these 5 valid answers that can be extracted from that from the corresponding image for this question. So in each epoch, the model would randomly receive one of these 5 answers, and the model eventually, if you fine-tune the model, let's say enough, like if you set a proper epoch, the model eventually would learn all this value, and it would learn how to extract the information from various parts of an image. So this is something that I wanted to address, but just keep it in mind that this is not going to happen in Cord v2, but it is a possible scenario. And in case your dataset has this characteristic and has this feature, now you know how to handle it. Perfect. So we just went through the data explorations. I'm not going to go through docvqa. It is simpler than Cord v2. You don't need that JSON to token function. You don't need that token to JSON function. It is just simply an answer. You just put it in the proper structure that the model expects. Let me see if I have it somewhere here. Here we go. So you just put it into a proper structure that the model expects, and you pass it to the data loader, and you can fine-tune the model. All right, so now it is time for fine-tuning the model. Let's go step by step and see how we can fine-tune it. In this notebook, the first thing that we want to do is to load the model and prepare the model, and also to create the train and validation datasets that we just saw how to create in the previous notebook. And also, just like the previous notebook, in order to fully understand what is happening inside this notebook, you need to be familiar with PyTorch, HuggingFace, and concepts such as parameter efficient fine-tuning and low-rank adaptation. These are some of the technical aspects that we are going to see in this notebook, and I'm not going to go into the details. So first, let's run and load the necessary libraries, and let's see what are the available GPUs on our machine. I have one A100 with 80 gigabytes. And then let's also set some of the necessary configs. I have the maximum length as 256. That is a decent value for Cord v2, but eventually you need to figure out a proper value for your own dataset. And just keep it in mind, the threshold would be the maximum allowed token for the model. So in case of LLAVA 7 billion, I believe it is 4096. Then we have the auto processor, and we want to load the processor here. And here we are just loading the model, and we are loading the quantized version of the model. So quantization eventually allows you to fine-tune the model on a smaller GPU with less computation needed for fine-tuning. And also, parameter efficient fine-tuning is again another technique that allows you to use less computation for fine-tuning. So the difference between parameter efficient fine-tuning versus full fine-tuning is, on full fine-tuning, we update all the weights of our model after calculating the loss. But in parameter efficient fine-tuning, we define a subset of layers in our model. We only fine-tune those layers and update the weights of those layers. And after the fine-tuning is done, we merge the weights to the original weights of our model. Okay, so let's run it as well. Perfect. So here we are going to create the train dataset and the validation dataset that we just created in the previous notebook. We already know what is happening here. And here I'm just printing 10 examples from the train dataset just to make sure we are on the right track. And here also I'm going to show the last image in these 10 samples just to make sure that everything is fine. Perfect. So up to this point, we just prepared the model, and we also created the train dataset and the validation dataset. So from here, we want to prepare the necessary functions, and let's say we want to go through the necessary steps for the fine-tuning itself. So first, we want to define these two functions. These two functions are designed for preparing the batches for training and evaluation. So they are almost identical with one key difference. I will just go through the description of this function and I will tell you what is the difference for the second one. This function prepares a batch of examples for training a model that processes both images and text prompts. The inputs are structured such that the model can learn to associate images with corresponding ground truth outputs. And here's the breakdown. The only difference between these two functions is that in the trained data, we have handle labels. So the input IDs of padding tokens are replaced with -100 in the labels to prevent the model from computing loss on them. So when we pass the training data to the model, we expect the pipeline to also calculate the loss for us. But when we pass the evaluate dataset to our model, we don't calculate loss on our validation data. So we don't have that step here. That is the only difference. Let's run these two functions. Perfect. So in the next step, we want to define a class that prepares the training, validation step, handles the optimizer, let's say define the optimizers, and also defines the data loaders. So let's define this class. We have the training step in this class that performs one training step. We have the validation step that performs one validation step. And again, pay attention, the training step returns the loss, but the validation step only returns the score. And we set the optimizer, and also we define the train data loader and validation data loaders. And here is where we want to pass the train dataset and validation dataset. And just keep it in mind, all the necessary changes on our dataset have already been applied, and the data that we have in train dataset and validation dataset are ready to be passed to the model. Next, we define the fine-tuning configs. So these are very well-known configs. I assume, again, you already know the meaning behind them. I have the maximum epochs here equal to 1, but I fine-tune the model on 10 epochs and save the weights already on HuggingFace. Then we also have the learning rate of 10 to the power of -4. What else? We have the batch size of 1, so we are passing one sample at a time. And here I'm defining a class for pushing the weights of the model after each epoch and also after fine-tuning is done into the HuggingFace hub. The only other thing is that in fine-tuning, you also would like to apply earlier stopping. Although usually when you fine-tune a model, you don't use a big number for epoch. So as I mentioned earlier, for this fine-tuning, I used epoch equal to 10. And the reason behind that is when you fine-tune the model, if you use a big epoch, eventually the model is going to somehow overfit on the dataset that you are passing to it and start forgetting what it learned in its training and fine-tuning stages. Let's say pre-training and the previous fine-tuning stages. We are calling it catastrophic forgetting, and that is a serious problem. Although the main question is, do you want to avoid catastrophic forgetting, or do you want to allow the model to overfit on your data? Sometimes, for instance, if you are designing or fine-tuning a model to become a chatbot and be able to answer specific questions to users, you really probably don't need the model to keep its previous knowledge. If it overfits on your data, that is still going to have a good performance. But sometimes, for instance, in this case, I didn't want the model to forget its previous knowledge, so we can also use the model to understand other images beside the receipts that we are going to pass to it. So that's it. And finally, we just define the trainer and run the trainer on the configs that we just defined earlier. So if you define the trainer, you would see that it starts to run on our dataset. Here also, I only took 100 samples from the training data just to show you how it works. So I will stop this fine-tuning process. And from here, if you allow your model, for instance, to fine-tune on 10 epochs and then push it on your HuggingFace hub, you would be able to load the model with the new weights and let's say the fine-tuned version of the model and start passing your images to it. So I already have the model ready on my HuggingFace. It is also public. You can access the model, you can load it, and you can test the model. And this is the way that you can load the model. I just have to double check the README file. I will check it and I will make sure that everything is in place. And in the next step, before designing the dashboard, let's quickly test the model's performance. So in this notebook, I'm going to load the fine-tuned model and I'm going to pass a few examples, a couple of examples, and we are going to watch the performance by ourselves. So here I'm loading all the necessary libraries. Then I'm passing the model ID along with my repo ID. And when I want to load the model, I would use the model that I pushed in my HuggingFace hub. So this is the function that I showed you earlier, and we are going to use it to convert the model's output and let's say create nicely formatted JSON data from it. So here I'm loading the dataset. I'm loading the validation split of our dataset, and this is an image in our validation data. Let's pass this image to our model and see the output of the model. So if we pass the image to our model, the model is going to give us something like this. This is exactly what we expected from the model. So this is the way that the model saw the ground truth. So now I can just pass this output to this function and get the JSON structure. So this is the expected response. This is the ground truth. And this is what the model gave us. Everything matches together. And just to give you an idea, this is the exact image that we passed to the 7 billion parameter model when it was not fine-tuned yet, and it said it is shady and I cannot understand the numbers inside it, and it asked us to pass it a text input instead. So this is the same image, and we can see that the model was able to perfectly give us the output for that image. Next, let's pass the second image. This is the second image that we passed to the 7 billion parameter model, and it said actually it refused to give us the answer, and it said there are personal information on that receipt. So this is the output that now the model has given us. So that is perfect again. If you compare the output versus the ground truth, you would see that the model was able to extract all the information accurately without any mistake. And this is another example. Let's see the difference here. So again, the model worked and performed flawlessly, and it was able to extract the JSON information and all the information from the image, and it 100% matches with the ground truth for that specific image. So we can see that the fine-tuning was successful, and our model is now able to extract information from the receipt that we are passing to it. So let's now check it on the dashboard side. So I have 3 modules in source folder: app.py, save sample data, and serve model. Let me first explain this one. So here I'm just loading the validation dataset of Cord V2, and I save 20 images in this folder named data. So I just wanted to be able to upload these images in the dashboard. Here I have a Flask application, and I'm going to serve my model on the Flask application. The reason behind that is if I put the model in a Streamlit application, whenever you make a change or whenever you upload a new file or whatever you do on the dashboard, Streamlit resets the whole app. So this app will be resets, and it's going to be executed again. So if you put the model and if you serve your model here, with every small action on your Streamlit dashboard, your model is going to be loaded again. So first, it's going to cause a lot of delay. And second, it's going to slowly occupy all your GPU up to a point where the model will not be able to run anymore. So I have served my model on a Flask application here. I have my token to JSON function technically whatever we saw on that notebook for testing the output, I have them here, but it is just running on a Flask app. And here I have my Streamlit module. So here I have the dashboard. As soon as the user uploads an image, it's going to send it to my backend, and my backend is going to receive it. It's going to pass it to the model, get the output, and convert the output to JSON and send it back to the dashboard. So let's test the dashboard quickly. So I can run the dashboard as Python source. First, let's serve the model, and also let's run the dashboard itself. So the dashboard is running on port 8501. This is a simple dashboard. I just wanted to show you how this model would perform. And on the other side, our model is also ready and we can upload an image. So let's upload an image here. Let's upload this one. So it just prepared the image, send it to the backend. And if I open here, we should see, so you can see that actually the model was initialized, and we see that we are getting the 200 here. So it successfully sent back the image, and now we can check the result. Perfect. So this is the image. We have a total of 2,000 and cache of 100,000 and change of 80,000, I believe. So these are the values. So we can see that we have the total 2,000, change 80, and cache price of 100,000. So we just saw how we can fine-tune LLAVA in order to extract JSON data from our images. You can also fine-tune LLAVA for different languages, for different tasks, and for other images to extract different piece of information from them. So you can fine-tune it for literally everything. LLAVA is an amazing open source multimodal large language model that you can use for your projects. So this is just a summary of what we had in this project. But I also wanted to show you the computation and the cost of fine-tuning LLAVA on those 10 epochs. So I chose LLAVA 1.6 Mistral 7 billion. I had one A100 with 80 gigabytes of GPU. This is the CPU on my virtual machine, and this is the RAM on my virtual machine. It took 142 minutes for my model to fine-tune with 10 epochs on 800 samples in Core V2, which was my training sample. And also I was evaluating with validation data after each epoch. So this is the configuration that you can keep in mind and just have a rough idea of what happened. We also applied parameter efficient fine-tuning, and we also applied quantization to our model. So these are all, they had big impacts on the performance, and everything overall costed less than $6 on my virtual machine. But of course, it's only for fine-tuning. So before fine-tuning, I also spent some time preparing the virtual machine, setting up the dependencies, playing around with the training configurations, and let's say some trial and errors. So overall, it costed around $30 to $40 until I fine-tuned LLAVA fully on those 10 epochs. And the best way to conclude the video would be, if you have a use case for LLAVA and if you want to fine-tune it for a specific task, it would be a very cost-effective model for fine-tuning, and you can expect great results from it. Thank you very much for watching the video, and I hope to see you in the next one.